Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. Welcome to my quantum physics video tutorial series. While we trudge through the world of wave-particle duality in this video tutorial series, why should we study the physics of blackbody? Well, one of the most crucial, complex, baffling and challenging theoretical concept in thermodynamics and quantum mechanics is blackbody. As a key cornerstone in quantum physics, it provides a profound and comprehensive insight into the fundamental mechanisms at the subatomic level. Its discovery revolutionized the field. The theoretical overview of blackbody radiation presented here in this video is a beginner's-friendly compilation of the fundamentals, rather than intricate mathematical approach. It's your ready answer paper. Save your time. Score high in exam. Alright, anyway. So the system temperature is the result of the constant collisions and motions of constituent particles. Now, a swift glance through conversion of internal thermal energy. Let's first talk about objects emitting, and hence, thermal radiation. Now, what about objects absorbing? You will find formal definitions in quotation marks. First, let's take a look at the discovery and definition. Kirchhoff firmly established the theory of spectrum analysis, a technique for chemical analysis by analyzing the light emitted by a heated material and applied to determine the composition of the sun. You will find formal definitions in quotation marks. I can tell what you guys are thinking. You are gonna say, it's difficult to imagine an object that absorbs and emits all wavelengths with equal probability, but not equal magnitude. After all, different wavelengths have different energies, right? The radiation system that's easiest to analyze is the inside of an empty box, so to speak, devoid of matter, to be precise. Let's imagine a hollow metal box with a blackened interior, with fortified impenetrable reflective walls, and a very tiny hole on the wall. This box is in thermal equilibrium, and is filled with radiation that bounces around inside the box, being repeatedly emitted and reflected by the metallic walls. The best practical blackbody is this black box, because practically none of the radiation entering such a hole could escape again, and the radiation would be absorbed inside the box. Let's assume that the temperature inside the box is above absolute zero. This means the inside is filled with electromagnetic radiation. It's a perfectly insulated enclosure in thermal equilibrium, internally containing blackbody radiation. It will emit through the hole in its wall, provided the hole is small enough to have a negligible effect upon the equilibrium. On the other hand, radiation from outside the box hits the hole and gets trapped inside the box, and is not likely to be re-emitted from that tiny hole. The only radiation that emerges from the hole is the radiation that has been bouncing around inside the box. This way, all the radiations would be absolutely completely trapped in this black box. This phenomenon is used by the Rayleigh-Jeans law. Experimental data performed on the black box showed slightly different results than what was expected by the Rayleigh-Jeans law. I'm gonna come to this law later in this video. graphic representation of spectral distribution of blackbody radiation at different temperatures. The curves in red, green, and blue correspond to different temperatures. The peaks of the emission intensity correspond to different frequencies that depend on the temperature. Mystery of light-emitting bodies represented an enormous challenge for contemporary physics. Blackbody radiation contradicted the theories of classical physics. In the late 1890s, calculations of the spectrum of blackbody radiation, based on classical electromagnetic theory and thermodynamics, ended up in major inconsistencies. Blackbody radiation was predicted by Gustav Kirchhoff. However, it was Max Planck who was able to correctly describe the behavior of blackbody radiation. Now, to comprehend the concept of anomaly or catastrophe, let's saunter through quanta, curve fitting, and infinity. In order to resolve such anomaly that the radiation energy would become infinite at infinite frequencies, Planck made the unprecedented assumption that energy comes only in discrete packets h nu. The Planck's constant h can be evaluated by fitting theoretical radiation spectra to the experimental ones. It was not until the end of the 19th century that Max Planck came up with an idea of quantization of radiation energy in attempt of solving the disagreement between theory and experiments. For very high frequencies, the kinetic energy is calculated as h nu. Please note that it cannot be translated into thermal energy at these frequencies, because this would mean infinite temperatures. Even though Rayleigh-Jeans law was widely accepted, the experimental results from the black box model, in reality, did not match all the way with the theoretical data. Well, we are naturally curious, did not match, in what way? Rayleigh-Jeans law states that the energy density of blackbody radiation can be estimated as a function of frequency, which changes with the square of that frequency. Rayleigh-Jeans law, also called Rayleigh-Jeans approximation, yields approximation of blackbody radiation curves at one of the two tails of the spectrum, the longer wavelength side to be specific. Whereas, Wien approximation has to do with the shorter wavelength tail of the blackbody spectrum. Rayleigh-Jeans law holds just fine for analysis at long wavelengths and low frequencies. However, unfortunately, that's not the case in analysis at short wavelengths and high frequencies. Ultraviolet catastrophe can be defined as the non-persisting behavior in classical physics between observations and predictions. Here you see graphical depictions of comparison between experimental results versus theoretical data, as well as classical versus quantum theories of blackbody radiation, shown in teal versus golden colors. The radiation can be in terms of intensity, plotted as a function of wavelength, and as a function of frequency. The Rayleigh-Jeans law fails to correctly reproduce experimental results. In the limit of shorter wavelengths, the Rayleigh-Jeans law predicts infinite radiation intensity, which is inconsistent with the experimental results. Radiation intensity has finite values in the ultraviolet region of the spectrum. This divergence between the results of classical theory and experiments is the ultraviolet catastrophe. It shows how classical physics fails to explain the mechanism of blackbody radiation. So, why is this paradox called ultraviolet catastrophe? The Rayleigh-Jeans law predicted that as the frequency of radiation increases, so would the emitted energy as well. At low frequencies, this equation matches experimental results, but at high frequencies it diverges sharply. These high frequencies are in the ultraviolet region of the electromagnetic spectrum, hence this was termed as the ultraviolet catastrophe. Let's start with a quick glance over the historic juncture, then saunter through what this law describes, some definitions, and the concept of quantization. Okay, well, hang on a sec. Yeah. Now that we have acknowledged the concept of quantization, we are able to ascertain the fact that when this quantized distribution is assumed, then the energy distribution of photons need to be expressed in a distinct manner, that is to say, not the way the Maxwell-Boltzmann distribution expresses the distribution of molecules as a function of energy. So, as you can see, this is how Planck function originated in the first place. Now that we have explored Planck's law, let's move on to the other radiation laws. By assessing blackbody emission curves at different temperatures, two crucial phenomenological laws were formulated from experimental observations, instead of, for instance, basic principles of nature. Wilhelm Wien explained blackbody radiation long before Max Planck. I would like to point out, it's quite practical, that the Stefan-Boltzmann law is easily observed by comparing the integrated value under the curves of the experimental blackbody radiation distribution at different temperatures. In 1884, Boltzmann derived this behavior from theory by applying classical thermodynamics and the black box hole concept, as demonstrated earlier in this video lesson. Okay, now, let's see how the radiation laws are related to each other. Here you see a law correlation as a function of wavelength and as a function of frequency. Illustration of a comparative analysis of the classical Rayleigh-Jeans law and Planck's quantum radiation formula in golden versus teal colors. The Rayleigh-Jeans curve agrees with the Planck's law for long wavelengths and low frequencies. Now that we have finished exploring three laws, here I'm gonna tell you a bit about Gustav Kirchhoff's genius idea. Let's now elaborate this statement a bit further. What's going to happen if we instead suppose a particular object can absorb better than it emits? Well, surrounded by a large group of objects, all at the same temperature, it will absorb radiation from the other bodies better than it radiates energy back to them. Here I am gonna describe laboratory construction of the simplest case of perfect emitter and perfect absorber related to the concept of trapped radiation, as well as what that leads to. While analyzing heat radiation, the simplest possible case would be an idealized object, which is a perfect absorber, and thereby a perfect emitter, conforming to our earlier argument. This leads to the observation that if an object absorbs 100% of the incident radiation, in turn it must re-radiate 100% as well. Bose-Einstein statistics was introduced for photons in 1920 by Indian Bengali mathematician and physicist Satyendra Nath Bose. It was generalized to atoms by Einstein in 1924. As you all are aware of, one of the great Indian Bengali scientists Bose's remarkable work on the blackbody radiation and derivation of Planck's law led to quantum statistics, in particular, photon statistics. Einstein applied Bose's idea to predict Bose-Einstein condensate, whereas Planck's blackbody radiation is one of the milestones in the history of physics. Planck's law is satisfactorily accounted for by recourse to Bose-Einstein statistics. Apart from chronological approach to the credits, and deriving one from the other, one has to broach this physics fallacy to serious intellectual debate. Well, nonetheless, Planck distribution must not be considered as a mere application of Bose-Einstein distribution. Planck originated his legendary quantum theory in 1900, and Bose-Einstein distribution was developed 24 years later. Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.